Hi, today we're going to be talking about measurement in assessment. We're going to be exploring what is called descriptive statistics. These are the mechanisms by which we convert scores from raw scores into standardized scores, which are the kinds of scores that are reported when we talk about standardized or norm reference tests. So grab your calculator. You're going to need it. And remember, you needed a calculator that has a square root button because you're going to need that as well. So let's talk about measurement and the standardization of measurement when we think about standardized tests. First of all, standardized assessment is something that's heavily used in the educational decision-making process. As much as we talk about all those other kinds of methods of assessment that are under that umbrella of assessment, we very often rely primarily on standardized kinds of testing to make our educational decisions, whether it's deciding whether someone's eligible for special education or deciding what kind of program or progress the student is making. So in order to understand standardized assessment, as an educator, you have to know several things. You have to know about how to select tests. You have to know the basic principles of measurement and how they apply to standardized testing. You have to know how to administer tests. You have to know about scoring procedures, how to score tests, and and then finally what the meaning of those various scores are. So today we're going to talk mostly about the basic principles of measurement, somewhat about scoring procedures, and then especially the meaning of various scores. Standardized assessment is based on the assumptions associated with the bell-shaped curve, and you're probably all familiar with that bell-shaped curve. That curve is based on the probability or the likelihood that the likelihood of high score occurring is similar to the likelihood of a low score occurring. And so what happens when you group scores together is you get a very few people at the high end of scores, similarly very few people at the low end of scores, and most people cluster around the middle. And to illustrate that, you could try this with a group of friends, get a bunch of people together, 10 to 12 is a good number, get a bunch of people together, and have everybody flip a coin 10 times. And write down the number of heads each person got when they flipped the coin 10 times, and graph these. And I think what you'll find if you do it enough times or you have enough people, what you are going to get is a distribution of scores that begins to look like a bell-shaped curve. So in other words, maybe a few people in your group are going to get mostly heads, so 9 or 10 heads when they flip the coin 10 times. And a small group of people are going to get 0 or 1 or 2 heads if they flip the coin 10 times. And most people are going to get a number of heads somewhere in the middle, like 4 or 5 or 6 heads when they flip the coin. So a bunch clustered in the middle and very few out on either side. That's what a bell-shaped curve is all about. Probability theory really talks about the bell-shaped curve, and it works very well with things like flipping a coin or throwing dice, games of chance. But the trouble with trying to apply that principle of probability to people is that people don't always conform the same way dice does. If you think about people and nature tends to play with loaded dice. And so rather than getting a nice smooth bell-shaped curve when we look at a group of people and we start to talk about their scores or their abilities or whatever, we might get clusters or bumps at one end or the other based on experiences that aren't part of the laws of nature. So more premature babies, for example, being born, or higher incidences of poverty, creating a lump at the negative end of the bell-shaped curve. And we can also get things that create a lump or a larger group at the high end of the bell-shaped curve. So children who have exposure to literacy kinds of experiences early on, for example, might create a bump of high scores on academic kinds of measures. So that's an important thing to remember, that people aren't dice or people aren't coins, but nevertheless, we apply the concept of bell-shaped curve to people. And we're going to talk about how we do that. So what happens is that we do statistical manipulations on standardized tests to allow us to make a group of scores on a given test convert into standard scores that represent the bell-shaped curve. And we start with a raw score. Well, a raw score is a simple score to talk about. You all know what a raw score is. We take the number of items on a test. We take how many items you got wrong. We subtract the number you got wrong from the number of items presented, and we get what your raw score is. So let's say there are, that there are 30 items on a test, and you got 15 correct, then your raw score would be 15. These scores are relatively meaningless by themselves. You don't really know what that means. And so in order to understand what they mean, we need to convert them into what are called derived scores. But let's keep talking about that raw score for a minute. Let's say you took the midterm, and you found out that your score on the midterm was 28. How do you feel? You should be saying, huh? And the next thing you should be saying is, well, out of how many? Because that's how we begin to understand the scores that we get. We ask, well, out of how many was that score? And I tell you that there were 30 items on the test. Well, now you're saying, well, that's not so bad because I can compute a percentage correct. That's an easy thing. I take the everyone knows how to compute a percent. So I look at what percent is 28 of 30. And that's pretty high. So you're going, I must have done well. And if the professor is grading on the curve, I'm high in terms of my score. If there were 50 items on the test and your score was 28, you're not feeling so good because now you've computed your percentage and you realize that your percentage was relatively low, your grade's likely to be a D or a C, and you're not feeling too good about that. But now I tell you that out of the group of students in the class that took the test, let's say there were 25 students in the class, out of the 25 students who took the test, most students got a score of 30. Now you're starting to compare yourself to other students and you're thinking, well, if most students got a score of 30, I don't look that good, comparatively speaking. So now what if I told you what your relative standing was in the class? And your relative standing out of 25 students was 24th out of 25. Now you're feeling really bad, and you know regardless of how the professor grades, you're likely to get a low score because compared to other students, your score doesn't look that good. So we talk about manipulating the score, first of all, in a number of simple ways that we understand to look at how you stand compared to other students in the class and compared also to a standard, which would be a grade in the class. When we talk about norm reference tests, what test makers have done is take scores based on a sample of students the same age or grade who attempted the same items, and they get what are called derived scores. And derived scores enable us to talk about a student's performance in much more meaningful ways than raw scores do. So derived scores are very important. In order to understand what a score really means, we need to compare it to other scores. We need to have a norm to reference it to. And that's what test makers create for us, is a set of norms to reference anyone's individual score to. They do it through a process called descriptive statistics. They take large sets of data and organize and understand that data through methods known as descriptive statistics. Derived scores obtain meaning from a large set of data or a large sample of scores. And by observing how a large sample of students the same age or grade performed on the same task, it becomes possible to compare any student with that larger group, and that's called normative evaluation. So let's go back to the midterm. If I had 25 students taking the midterm, I could use their scores, their raw scores, and convert them to create meaningful derived scores against which I can compare future students in this class when they take the midterm. So I can compare how they performed against how you perform. So I could use you all as my normative group and do some conversions on your scores on the midterm in order to be able to talk about a number of different things. And we're going to be looking at how we convert those raw scores and how we convert them into meaningful scores that most people would be able to understand, or at least most educators should be able to understand. The first step would be to take that group of scores. So in this example, I could take the group of midterm scores from all of you and then graph them to see how they are distributed. In other words, I would look at how many people got each kind of score and put them on a graph, and I'll show you an example of that in a bit, and look at whether or not your scores conform to what looks like a bell-shaped curve. That's the first thing I want to look at. It's called eyeballing the data. So I want to eyeball my data, and hopefully what I get when I do that is that your scores distribute normatively. In other words, most of you will cluster around the mean or average score. Some of you will score very high, and some of you, unfortunately, will score very low, and your cluster of scores will look like a bell-shaped curve. And hopefully that's what I get. It's not, however, always what you get. And in grad school, I hope it's not what I get. I hope I get a set of scores on the midterm in which most people get high scores and very, very few get low scores. And that would be a skewed distribution. So let's talk about some of the terminology that's used when we graph scores and eyeball them to see if they fall into that bell-shaped curve. We can characterize the distribution of scores in a couple of different ways. Number one, we can talk about the mean or the average score. And that's a score that divides the group in half. So half will be above average and half will be below average. We can also talk about the variance, how spread out the scores are around the mean. They can be very spread out or they can cluster right around the mean. We can talk about the skew, and I just mentioned the word skew. I would hope that in a graduate level course, there is a skew on the midterm, and that is what is be known as a negative skew. In other words, fewer people would be out in the negative side of the bell-shaped curve, and most people would be on the positive side of the bell-shaped curve. In other words, most people would be A's and B's, and fewer and fewer and fewer people would be getting lower grades. But that's not a bell-shaped curve. Nevertheless, I can make it into one, and we're going to see how that happens as we go along. And the final term that we use to talk about distribution is the term kurtosis, and that is also peakedness. So how does the bell-shaped curve rise around the mean? Is it something that looks like this? So in other words, almost all the scores cluster around the mean, and we get very little distribution out on either end. Or is there a spread of scores such that it's a lower lump around the mean and scores spread out further and further and further around the mean? Now, if you look at your text and you look at that reading, especially that I gave you, you will see descriptions and pictures of what those terms mean. So I recommend that you do that. So we eyeball the scores by graphing them. And then what we do is use descriptive statistics to manipulate raw scores into standard scores, which include percentile rank, other kinds of standard scores, which we'll be talking about as we go along, z-scores, t-scores, Stanines, and so forth. Grade equivalence scores, probably that's the one that you're most familiar with. It's the one I like the least. Age equivalence, I don't like those either, but you're probably also familiar with those. And then something that's pretty standard in academics, which is a quotient. So you'll see very often when we're at IEP meetings or we're scoring a standardized test that the resulting standard scores that we get are what I call Q scores. This is what the bell-shaped curve looks like, and this is what we hope to see with our normative group, the sample group that we get our derived scores from. We hope to see a normal distribution of scores, and we base everything on that, and if our graph doesn't look like that, we force the scores into this bell-shaped curve. So the bell-shaped curve, as you can see, is divided up, first of all, into mean. So the mean test score is calculated, first of all. The mean is the score that divides the bell-shaped curve directly in half. So the first comparisons that we can begin to make when we start to calculate statistically numbers that relate to standard scores, the first thing we talk about is the mean. So I could take your midterm scores, for example. I can calculate the mean score, and you probably all know how to do that. We'll be doing it as we go along, but basically it's all of your scores together divided by the number of people in the class. That gives me the mean score, or the middle of the bell-shaped curve, and now I can talk about who scored above the mean or above average, and who scored below the mean or below average. But that's not very satisfying. It's some information, and it's more information than just what your score is. But you probably want to know also how far below average was your score. So we begin to divide the bell-shaped curve up into finer and finer divisions, and those divisions are called standard deviations. So we go one standard deviation above the mean, so where you see plus one's SD, that's plus means going in the positive direction or above the mean. So we can go one standard deviation above, two standard deviations above, continue to slice that curve up. We could go 3 or 4. Mostly we'll be using 2, possibly 3 standard deviations when we do our calculations later on. We can also go 1 standard deviation below the mean, 2 standard deviations below the mean, and so on. And once we are talking about a normative evaluation or a normal curve, we know with accuracy what percentage of scores or people fall within each standard deviation unit. Now, as I talk about it, I'm going to round out the numbers, but the numbers that are on the bell-shaped curve that you see are a little bit more statistically accurate. I'm satisfied with rounding them out. So within the mean and 1 standard deviation above the mean, you see that approximately 34% of the population, or 34% of the scores, lie within that standard deviation unit. And similarly, because this is a symmetrical curve, a true bell-shaped curve is symmetrical. It's the same on both sides. Within the mean and 1 standard deviation below the mean, again, there's about 34% of the population or the set of scores. So we could say 68% of the scores, or the population roughly, will be considered average. So the largest number of people in a population or a group of people taking a test should cluster around the mean within 1 standard deviation, and they are average. Think about it in terms of that's your C group. Now, within 1 standard deviation above and 2 standard deviations above the mean, we capture about 14% of the population. So 14% of the population, or scores, would be considered to be above average, and many tests will report out their results in that way. So we can tell whether your score is in the above average range or not. And likewise, on the other side, if you're one standard deviation below, within 1 and 2 standard deviations below the mean, again, it's about 14% of the scores or 14% of the population would be considered below average. Now, still, that's okay. So if you're within 2 standard deviations above or below the mean, you're still in a range that's considered average. Most of those students are going to be in the general ed classroom. Some are doing better than others, but they wouldn't be considered necessarily special education students, except with the exception of learning disabilities, which we'll be talking about more as we go along. Now, if you go 2 standard deviations or more above the mean, which is about 2% of the population, you're talking about students who fall into what would be considered the gifted range or the significantly above average range. So about 2% of the population is significantly above average. If we were talking about cognitive ability, those would be the students that we might label as gifted. And on the other side of it, if you're 2 standard deviations or more below the mean, that's roughly 2% of the scores or the population. That group of students or scores would be considered significantly below average, and that might get you the label of cognitive impairment. So if we're looking simply at scores, that's one way to think about it. So instantly you should be saying to yourself, okay, if I hear a score that is 1 standard deviation above the mean, I know I'm dealing with an average student. If I hear a score that's more than 2 standard deviations below the mean, I know that I'm dealing with a student that may need significant help. And we're going to be able to slice this normal curve into more and more finer divisions. But this is the basic way that we tend to think about the curve. So I want you to have this as a reference and use it. Sleep with it. So that you really have that picture in your mind so you can begin to understand where students fall. So now we're going to learn how to divide the normal curve up using formulas for mean and standard deviation. So you see here on this slide, the mean is the average score or the middle of the distribution. And I've given you the formula for that, even though you probably already know how to do it. But the formula, don't be afraid of the formula. It just has some funny symbols in it. And once you understand what those symbols mean, you can easily compute these, you can solve these formulas. So what you have is mean equals the sum. So that funny looking symbol that looks somewhat like an E is the symbol for sum. The sum of scores, X means scores. So the sum of the scores in a test, so let's say if we're talking about the midterm, the sum of all the midterm scores divided by N. N means the number of scores. So how many people took the test? What were their scores? We're going to sum up their scores. We're going to divide it by the number of people who took the test, and we have the mean for the test. So that's the first thing that we do. And the next thing that we do looks a little bit more complicated, but there's actually no more symbols except for one than what we're already used to. So we have SD as the standard deviation is equal to, and you see that funny little sign that looks like a check mark? That's the symbol for square root. And if you remember, I asked you to have a calculator that has a square root button. That is the last function that we'll do when we solve this formula, but it's an important one. So the formula says the square root of the sum of all the scores squared. Scores squared. Well, that means that we take all of the scores that we have and we square those scores and we add them up and we get a number that is the sum of all of those squared scores. That's the number that we're going to put in there. And then it's minus, and in parentheses we have the sum of the scores. Well, that looks like the same symbol as we had when we were talking about the mean. So that means we're going to sum up all the scores. And we'll have a number to put in there. And later on we're going to square that number. And we're going to divide it by n. N being the number of scores. And then we're going to divide, we're going to do all those calculations, and we're going to then divide what number we get by n minus 1. So we'll get a new number. Then we're going to push our square root button, and we'll have the answer. We'll have the standard deviation. So I'm going to say it one more time. The standard deviation is equal to the square root of the sum of all the squared scores minus the sum of the scores squared divided by n. The whole thing divided by n minus 1, and then that number we get the square root of. And now we're going to practice that. You have a worksheet that you can download from Moodle, and it looks like this. It's the mean and standard deviation worksheet. And on that worksheet, you have a number of scores. There are 15 scores total on a reading test. And the maximum score on that test could be 30. That's something to remember later on. So what we're going to do first, and I'm going to get my paper out so I can do it too. We're going to list all of the scores in the first column on the left where it says scores or X. We're going to list every single score. So I'm going to start by finding I'm going to go from the highest score to the lowest score, so I make sure I have them all. I'm going to start with the highest score, and looking at the set of scores, I see that the highest score is 25. So number 1 is 25. I keep looking at my list and I see another person got 25. So number 2 is 25 because every score gets listed. Number 3, I look at my list and I see, oh, there's another person that got 25. So far 3 people got 25. 1, 2, and 3 are the score of 25. My next score, the next score is 24. 1 person got that, so number 4 is 24, and so on. So I'm going to continue to make the list and get every single score that's listed in the list of scores, with number 15 being the lowest score, and just looking at it, the lowest score should be 9. So pause this slide, go ahead and make your list of all of the scores. Okay, finished? Ready? So you have a list of scores, 15 scores in the list. And now you see at the bottom, it says total, or the sum of X, the sum of the scores. So again, pause the slide, take a moment, and add up all 15 scores and see what number you get. Okay? Ready? I did it. I got 307. How about you? So 307 is the correct answer. Why don't you take a moment and just get the mean of scores then. So take 307 and divide it by the number of scores, which is 15, and that will give you the mean score. I got 20.5. How about you? So the mean score, and the symbol for mean, by the way, just so you have all of your symbols down, would be X with a line over the top. So when you see X score with a line over the top, that means mean score. So go ahead and enter that onto your paper. X with a line over the top, mean equals 307. And not 307, but 20.5. I'm sorry. 307 is the total of the scores. Divided by 15 gives us 20.5. 20.5 is our mean score. Now we're going to move over to the column on the right where it says squared scores, or X squared in the parentheses, and we're going to go ahead and square all of the scores in our list of scores. So I'm going to look at the first score, which is 25, and I'm going to square that score. Squaring a score means that we multiply it by itself. So when I square 25, I get 625. My next score is 25. I'm going to square that. I also get 625, so I put that down. My third score is 25. Again, 625. I'm going to put that down. And my next score is 24. I'm going to square that, and I get 576. I'm going to put that down. So you go ahead and do that. Square all of the scores in your list. And when you're finished, take a moment to add up all of those scores and enter that in the total of the scores squared. So square them all and then add them up. So pause the slide and come back when you're done. Ready? When I added up all of those squared scores, I got 6,551. So if you didn't get that, go back and add your numbers again. Sometimes we get lost adding the numbers up, and a simple push the wrong button on those calculators and you can get a different score. But you should get 6,551 as the sum of all the squared scores. Now we're going to go back to our formula. So you have those numbers in front of you, and we're going to plug them into our formula. So the first number that I have that I can replace the symbols with is I have the sum of all the squared scores. And the sum of all the squared scores, remember, is 6,551. And I'm going to replace those symbols then with 6,551. With me so far? And I'm going to move over and I see the sum of the scores. Well, I did that too, so I'm going to replace those symbols with 307 because that was the sum of all the scores. And in a moment I'm going to square that, but right now I'm just plugging numbers into the formula. So I have 6,551 minus 307, which is going to be squared, divided by n. Now, what is n? That's the number of scores. So in place of n, I'm going to put in a 15. And I'm going to move down where I see an n again, and I'm going to put in a 15. So now I have 6,551 minus 307, which is going to be squared, divided by 15, and that whole result is going to be divided by n minus 1. And now I can begin to perform my calculations and calculate the standard deviation. And remember, after you do all of this, first you're going to square the sum of the scores. You're going to square 307, get a number which you'll divide by n. You'll divide that by 15. So you'll have a number there, and you're going to subtract that number from the sum of all the squared scores. Okay, and then you're going to divide your result by n minus 1, which will be 15. And so you'll get down to one number, and then you're going to push the square root button, and you will have your standard deviation. So take a moment, do those calculations, and get the standard deviation. Ready? My calculations tell me that the standard deviation is 4.4. So we have a mean of 20.5 for this group of scores, and we have a standard deviation of 4.4. Now, we didn't eyeball these scores yet, so I wanted to take some time to do that before we go any further. Let's see if this set of scores looks like a bell-shaped curve. Well, I went ahead and charted the scores, and this is what you can do. The vertical axis lists the number of people getting a score. So even though it's divided into decimals, one person getting a score, two people getting a score, three people getting a score, and so on. And the horizontal axis, I've clustered the scores into groups of 2. So where you see number 1, I started with the lowest score, 9, and I clustered it. So 9, 10. Number 2 represents 11, 12. Number 3 represents 13, 14. Number 4 represents 15, 16, and so on. And then I simply plotted the number of people getting each of those scores within that cluster. So if you look at down at number 1 representing the scores 9 and 10, one person got a score between 9 and 10, or of 9 or 10. Then we go to the next set of scores, which would be 11, 12. Nobody got 11, 12. 13, 14 would be number 3. Nobody got 13, 14. Number 4 is 15, 16. And we look at that and we see one person got a score of 15 or 16. 17 or 18, 3 people got a score of 17 or 18, and so on. So you can see how I charted the scores or graphed the scores so I could eyeball them. Now, when I eyeball scores, I'm asking the question, does that look like a bell-shaped curve? Does that look like a bell-shaped curve to you? Because it doesn't look like one to me. It looks like a curve that is skewed. So remember that term? And if you looked back at the book and you looked at the reading that I gave you, you understand, or you should be saying to yourself, that's a skewed curve, or that's a skewed set of scores, and that set of scores is skewed negatively because there are fewer and fewer scores going out to the negative end of average. And you see that it drops off abruptly at the top. Nobody got a score above 25. So even though we could have gone further with our numbers and clustering the scores, nobody got a score higher than 25, even though the possibility was 30. This is a slightly negatively skewed group of scores. It doesn't look like a bell-shaped curve. So that says to me the group of students that I used to test this test on isn't a normally distributed group of students. In fact, they, in general, tended to do fairly well on the test, and only a few people did poorly. But nevertheless, I'm going to force those scores into a bell-shaped curve. And here's a picture of what that looks like when you force the scores into the bell-shaped curve. As you can see on this picture, what I did was I drew my bell-shaped curve, and I put in my standard deviation lines above and below the mean, and I plugged my scores in. So my mean score, which I plugged in, is 20.5. That was our mean. Then I add the standard deviation and I subtract the standard deviation depending on the side to get scores at each of the standard deviation lines. So one standard deviation above the mean is 24.9. 2 standard deviations above the mean is 29.3. Now I go below the mean. 1 standard deviation below the mean, I'm going to subtract 4.4. I get 16.1. 2 standard deviations below the mean, I'm going to subtract another 4.4, and I get 11.7. So are you with me so far? Why do I bother to do that? Well, now I can talk about more than just whether you scored above average or below average on my test. I can pinpoint how far above or below you actually are simply based on raw scores. So how would I characterize a raw score of 25? A raw score of 25, I'm thinking to myself, I close my eyes, I think about that bell-shaped curve and how I force the numbers into it. A raw score of 25 is roughly 1 standard deviation above the mean. So that particular person who got a score of 25 is beginning to fall into, is just really barely in the above average group, but that's where they are. They're a little bit more than 1 standard deviation, very tiny bit, more than 1 standard deviation above the mean. And then if I think about that student who got a score of 9, or anyone else who comes along and gets a score of 9 for that matter, where would a score of 9 place you? Well, we didn't move it out more than 2 standard deviations above and below, but if I think about where that score of 9 is going to fall, I could say that that score of 9 is likely to fall between 2 and 3 standard deviations below the mean. So that's person or anyone who gets a score of 9 on that reading test is certainly displaying some significant reading problems because they are more than 2 standard deviations below the mean. So now I can talk about your relative standing on the bell-shaped curve related to that test, how you compare to my normative group, which was that group of students, that 15 students that took the test to begin with. And I can begin to say things about, or potentially say things about your reading ability. It was a small group, but it has now become my normative group. So let's move on. We can now convert the scores because, and why would we do this? I'm going to go back to that slide for a moment. We know because you just did the calculations, you know based on how we force numbers into a bell-shaped curve, if you were to take somebody's score into an IEP meeting and they got a score of 12, let's say, on that test, you would know where they fell on the bell-shaped curve and be able to talk about them as being somewhat below average. Nobody else would know, however, what the mean of that test was or what the standard deviation of that test was. So we would have to convert those scores now that we have into scores that everyone can understand. And here are some of the kinds of conversion scores that we would want to talk about.